Problem 1. This is a problem about a completely randomized design. We are going to use a robot in this experiment. Suppose that USGA, United States Golf Association, wants to compare the mean distance reach of 4 different brands of golf balls struck with a driver. This is a special club. A completely randomized design is employed with iron beyond the USGA's robotic golfer, using a driver to hit a random sample of 10 balls of each brand in a random sequence. The distance is recorded for each hit, and the results are shown in table 10.3 organized by brand. That is the result. First question will be, set up the test to compare the mean distance for the 4 brands. Use alpha 0.10. This is the significant level. Alpha is equivalent to the type 1 error, is the error that this researcher is willing to take, 10% of the cases when he selects samples. Part B, use statistical software to obtain the test statistic and p-value if the appropriate conclusion. You have in MyStabLab this data with this little icon that appear above the data. Then you have to click this data and you can send this data to Excel and StatCrunch. We have to send the data to both software in order to work with this kind of problem. First of all, let's send this data to MyStabLab. And this is my data in MyStabLab. Then, how can we obtain my Anova table in MyStabLab? Click Stat. In Stat, I have to select Anova. In Anova, we have select one way because actually here we have only one factor. Only one factor is the brand of the ball. It's the only thing. The variable that we are studying, in this case, is the distance that each ball reach after it is hit by the driver, the club. We want to compare the mean that each brand ball reach when is hit by the driver. And we use Anova. It's one table, only one factor, brand. Later we are going to study when we combine brand with different club. All ball will be hit using the same driver. Let's select one way because we have only one factor. And we are going to select all of these brands which represent the different level of this factor. We want to compare the mean distance that each brand reach under the same impulse. Also, later we are going to use Toolkit to compare all of this mean, but right now, if we click compute, we obtain the Anova table, which is this one. This is the Anova table, and this is the summary of all means. We are going to obtain all of these numbers manually using formulas and table. How can we do that? When we send this information to Excel, we have this data here. Then we have to obtain the sum, basically to use formulas, the shortcut formulas given in the last pages of the book, and I gave this formula also in the PowerPoints. We need to sum all of these columns. To sum all of these columns, we have to start here, write equal, and sum of all of these values. And click. That is the sum of the first column, and we can drag this formula to these other boxes, and we can obtain the sum of all of these columns. That is the value that we need to use formulas and table. This is another printout because I can obtain from MyStabLab this drawing in order to understand better this data. We have here different brands. We have the brand A, that is the distance reached for brand A, brand B, brand C, and brand D. Actually, there is a difference between them. When you see this graphically, you can observe different. For example, this brand reached the highest distance. But let's verify this statistically. That is the table that we want to construct using formulas and table. We have already this in Excel. Let's complete this table using the formulas. The first thing that we have to obtain is the correction factor. Is given by the sum, listen, the sum of all y squared divided by n. Remember that this correction is needed because we compare variance. We are going to compare variation respect to the mean. Remember, when we want to obtain the deviation of each value respect to the mean, and we want to sum all this square deviation, there is a shortcut formula to obtain this. We can develop this square and apply some property, and we can obtain this shortcut formula. The sum of all values squared minus the correction fact, the correction that is given by the sum of all x squared divided by n. That is a shortcut formula for this formula, the sum of all deviation squared. That is the correction value. To obtain this correction value, we need to obtain the square of all of these values. We need to sum all of these values and square this quantity. How can we obtain the sum of all of these values? Let's go to Excel, and in Excel, let's input in this box equal the sum of all value from this point to this point, and equal. That is the sum of all values. We need to square this quantity to obtain the correction. Then we need to input this value here, and we need to divide this value by 40. Then let's obtain the total sum of a square deviation with respect to the overall. Then this total sum of a square is given using the shortcut formula, but the sum of each value is squared. So we need to square each of these values, and after that sum all of them, and we need to subtract the correction. Remember, this total sum of a square with respect to the means, we can obtain the mean of all of these values, adding and divided by 40. And if we want to obtain this each value minus this mean squared. This formula is equivalent to this, but it's a shortcut. It's better to use this one because we avoid several errors, because we need to round this quantity. How can we obtain the sum of all square values? We have here values, but not the square. The sum of all square value, we have to copy here this value raised to the second power, and this formula must be copied in all of these cells, and also we can copy all of these in these other cells. We have the square of all values in seconds. How can we obtain the sum of all these square values? Then the same thing, equal the sum, open parentheses, of all value from this cell to this other cell and click. That is the sum of all square values. And let's return to our, then we need to plot these values there to 2,661,000 minus the correction. That is equal the sum of a square total respect to the overall mean is 3,556. We need to input this value here in this point, and the degree of freedom of this will be equal n minus 1. Because we have n values, the degree of freedom will be n minus 1, 39. Then the sum of a square treatment, we need to obtain the mean of all of this value. We need to divide this by n, the mean of all of this value, and we are going to obtain the deviation of all of this mean respect to the overall mean. That is the sum of a square treatment. That is the original formula. We have the mean for the first treatment minus the overall mean. The overall mean will be obtained adding all of this value and divided by the total 40. We are going to square this distance and sum all of this square, but this mean is the mean of all of these 10 results. Then this mean represents 10 results, N1. For that reason, the original formula is this one. But the shortcut formula, if we develop this, we will obtain the shortcut formula. We are going to sum all of this value in this column, and we are going to square that and divide it by N1, plus the sum of the square of the second column divided by M2, and so on, minus the correction. That is a shortcut formula for this expression, the shortcut formula. Then where this quantity T1 is the sum of all value in this column, and we need to square this distance, and Cn is the correction value. Let's substitute all of this expression in my formula, and you see here is the third brand. The sum of all of these results should be a square and divided by 10, because we have 10 observations here. Then when we compute all of this, we will obtain the sum of a square treatment is equal to 2,794. The degree of freedom for sum of a square treatment because we use in the original formula, we use only 4 means. We have 4 means, then the degree of freedom should be 4 minus 1. 4 minus 1 will be my degree of freedom, will be 3. And we need to write this value here and here for the degree of freedom. That is treatment, in this case, brands. To obtain the sum of a square error, the sum should be obtained each value minus the mean of each treatment one, each value minus the treatment one. Then we need to square this value, sum of all of these, but we have to do it with all of these values. All of these values, we need to obtain the deviation of all of these values with respect to the mean of this treatment. We are going to do the same for this, the deviation of all of these values with respect to the mean of this second treatment. This is the first one, this is the second one, and so on. And after that, we are going to sum all of this. That is the formula for the sum of square error, because the sum of square total is split in sum of a square treatment plus sum of a square error. The sum of a square error, the shortcut formula, is the total minus the sum of square treatment. We have these two values, and this is 7.62. Then we need to input this value exactly here, error and the degree of freedom, because we use 4 means to obtain this deviation. Then we have 40 value minus 4 means, that in this case will be equal to 36. Then in order to compare this variation, the variation for the sum of a square error and the sum of a square treatment, we have to obtain the mean, so the mean square treatment and the mean square error. The mean of a square treatment and the mean of a square error both are variance. For that reason, this procedure received the name of analysis of variance, or ANOVA. The mean of a square treatment measured the variation between treatment, and the mean of a square error measured the variation within each treatment for all treatments. And the mean square treatment is given by the sum of a square treatment divided by the degree of freedom, its corresponding degree of freedom. And in this case, will be given by 2,794 divided by 3. It will be 931. This value should be written here in this position, mean square treatment. And after that, let's compute the mean square for error and input this value here. The mean square for error is given the sum of square error divided by n minus k. After that, we need to obtain my test statistic. In my test statistics, I compare the mean of square treatment with the mean of square error. When we compare these two values, we divide it, we obtain this test statistic. We divided the mean of a square treatment by the mean of square error to obtain 43. This is my test statistic. We are going to obtain the p-value later in the next slide. Then that is the way that you need to show your work using formulas and table, and also you need to write all of these steps. To compare the mean distance of the 4 brands, we first specify the hypothesis to be tested. We are going to assume that all means for all different brands are equal. Mu1 is equal to mu2, mu3, and mu4. 4 different brands. Let's assume that the distance reached for all of these brands will be the same. And what is the alternative? Any statement that denies the first one. At least one is different to the other, or 2 of them, at least 2 of them are different. The test statistic compares the variation among the 4 treatment means with the sampling variability within each treatment, then that is F, obtained from my ANOVA table. My test statistic is F, and this test statistic was given 43 point something. The F distribution was obtained when we select several samples of the same population or population with the same mean, and we compute the F statistic using ANOVA table, and we are expecting that if all populations have the same mean, when we compute the F statistic, we are expecting a value close to 1, around 1, but not so big. This test statistic detects when one sample was obtained from a different population. How can we obtain my rejection region given alpha? If this is alpha, I need to find this critical value, F sub alpha, using the F table. And my rejection region is given in this case by, we need to find this value in the table. Or we can use technology if you want. Find this value in the table, we need the degree of freedom of numerator and the degree of freedom of the denominator to compare my evidence with my reference point obtained here. We need to find this value, F sub alpha, with this degree of freedom, for which we have in this table 10%. We have different table for F distribution. That is the table that gives me this critical value when this tail is 10%. In this table, we have all of these possibility for F distribution. Then the degree of freedom of our numerator was 3, and the degree of freedom of our denominator was 36. Then the corresponding critical value will be located between 30 and 40 because this table is incomplete. Then will be a value between 2.23 and 2.28. If we use technology to find this value, we can go to StatCrunch, and in StatCrunch we need to go to Stat, Calculator, F, and we can obtain this. Let's do it. Let's go to StatCrunch, Calculator, F distribution, and degree of freedom of the numerator will be 3, and the degree of freedom of the denominator will be 36. And here we need to input the tail, which is 0.10, and this should be the tail to the right. And when we click compute, we obtain this critical value. This value is 2.24.26. That is the exact critical value. This is my critical value. My evidence in this case was 43. My evidence actually falls far away from my critical value to the right. For that reason, we have enough evidence to reject the assumption. The assumption, because we obtain this distribution when we assume that all brands have the same mean. Assuming that, we can obtain that distribution. But in this distribution, to obtain one value like this actually is very difficult. It's almost impossible. For that reason, we can use this evidence to assure that the assumption, this assumption, is not true. This assumption is not true. Then at least one mean is different. That is, how can we obtain the p-value of 43? We need to input 43 in this box and click compute. When we click compute, that is the p-value. The probability to get one value equal to 43 or more extreme in the direction of my alternative hypothesis. Actually, this value here is a value very close to 0. This 12 exponent means it's 12. 10 raised to the negative 12 exponent means that the point should be located 12 spaces to the left, like this. Actually, that is the meaning of this negative exponent. This value, when you round this value to using only 3 decimal or 4 decimal or 5 decimal, this value is 0. And we reject the null hypothesis at alpha 0.10% level of significance, and we conclude that at least 2 of the brands differ with respect to the mean distance traveled when struck by the driver. That is our conclusion. We can obtain this conclusion only from the printout looking at p-value. If the p-value is 0, it's because my evidence falls far away from my expectation. Okay, let's verify the assumption in this case. Which one are my assumptions in order to use this procedure? The first one is that we need to select a random sample from all brands. The sample of golf ball for each brand are selected randomly and independently. Second, the probability distribution of distance for each brand are normal. Inside each brand, the distribution of all distance reached for each brand is normally distributed. And that third condition is very important. The variance of the distance probability distribution for each brand are equal. The first one, we assume that the first one was all 10 balls from each brand were selected randomly. The second one, the probability distribution, we have to use, in this course, we are going to use graphical procedure. We can use either histogram or box plot. And for the last one, we can use a graphical procedure using box plot to compare the standard deviation. To verify that the distribution inside each brand is normally distributed. Can you see this histogram look pretty normal? This doesn't look normal, but we can depart a little bit from the normality condition, a little bit, and the procedure is valid. But the way to do that is using box plot. In box plot, we can observe here that the interquartile distance is this one. That is the interquartile distance. And if we have no outlier, then, for example, here we notice that we have no outlier because 1.5 interquartile distance, we have a fence here and a fence here. There is no any observation outside those fences. There is no observation outside the fences. Here also, this is the interquartile distance, then 1.5, the fence is here and the fence is here. We have no outlier. The exception is only this distribution. In this distribution, the interquartile distance, we have 1.5. Here we have a fence and here we have another fence. Actually, as you can see in brand D, we have one observation that is far away from the rest. This is an outlier. In this condition, we can, when we have no outlier, we can state that these distributions are pretty normal. But the exception is the one, but we can, despite of this, we can use this procedure because we depart a little bit from normality. And also we can compare the interquartile distance in order to make a conclusion about the standard deviation, because all of these boxes are pretty similar. We can conclude that the standard deviation are equal. The standard deviation of the population, because this is the standard deviation of samples. In this way, we can verify our condition. And you can read this from the PowerPoint.